Man Energy Solutions is increasingly relying on predictive, digitally validated manufacturing supported by VERICUT. The software simulates all CNC machining operations before they reach the shop floor, preventing collisions, tool failures, and access over travel. By accurately modeling machine kinematics, work-holding systems, and tool libraries, VERICUT enables optimization of NC programs, adjustment of cutting parameters, and reduction of cycle times. This virtual verification improves process reliability, part quality, and overall machine availability. Combined with Man's stringent production standards, VERICUT provides a robust foundation for efficient, repeatable, and high-performance large engine manufacturing.
The VERICUT milling machine precisely removes material from a metal workpiece using a rotating cutting tool, shaping it into the desired form. The Garutspe heavy-duty lathe rotates large metal parts while a stationary cutting tool shapes them, ensuring high precision in turning operations. The SMX 2100 is a high-precision, multitasking turning center designed for complex machining. Its workflow begins with securing the workpiece in the chuck. The machine then performs turning operations using the main spindle, followed by milling and drilling with the B-axis head. The sub-spindle enables simultaneous machining on both ends of the part. Advanced automation and synchronized tool changes enhance efficiency and accuracy, making it ideal for producing intricate components in a single setup.
Inside the Saint-Marcel plant, one of the world's leading centers for heavy nuclear component manufacturing, the creation of primary parts for EPR steam generators is a display of engineering mastery. Spacer plates are drilled, inspected, and machined to exact tolerances. In the vast medium bay, stretching 300 meters in length and towering 30 meters high, a 350-ton crane moves massive structures into place, while inconel cladding is expertly applied to steam generator tube sheets for the Hinkley Point C project. Digitalized NEO 3D workstations streamline operations and ensure perfect accuracy. In the heavy bay, with its 600-ton lifting capacity, automated and manual welding unite the vessel shell nozzles, while massive lower sections and conical segments are machined for flawless assembly. Each 1300 MW steam generator undergoes hydraulic testing before shipment, its surface protected by peelable varnish, a testament to industrial excellence.
At the Horn Foundry, recycled metals are sorted, melted in high-temperature furnaces, and cast into new components, ensuring material purity and quality. At the CCR refinery, spent catalysts undergo continuous regeneration. They are oxidized to remove carbon deposits, reduced to restore activity, and reintroduced into the process, maintaining efficiency and minimizing waste. The brass production process at the Saint-Just-des-Vernes factory involves melting copper and zinc in a furnace, then casting the molten alloy into molds. After cooling, the solidified brass is removed and subjected to rolling, cutting, and polishing to achieve the desired shape and finish. Automation and reinforcement production at Rikers Bettenwerk demonstrates a technically sophisticated integration of robotics and digital logistics. At the core of this setup is a high-performance mesh welding system, supported by 3 robot-assisted stirrup benders. Each bender is equipped with automated tool-changing capability. Robots not only extract the stirrups, but also switch bending heads autonomously, ensuring continuous, precise operation without manual intervention. The reinforcement cages for wall panels require exact stirrup shapes delivered just in time. To achieve this, the system features intelligent logistics that track and place bent stirrups onto dedicated processing frames. These frames are moved within the hall by digitally coordinated forklifts, receiving real-time data from the central system to avoid delays and errors. The robotic workflow ensures that each stirrup is produced, placed, and transported with minimal tolerance deviation. The bending tools and mesh welding stations are fully synchronized, creating a frictionless production flow. This level of automation not only improves production accuracy and reliability, but also compensates for labor shortages. Through this integrated approach with Progress Group, Reker's Bettenwork significantly boosts efficiency, output stability, and technical precision across its reinforcement production line. The process begins with heating brass billets to 800 degrees Celsius. These billets are then forged into shape using high-pressure molds. Subsequent CNC machining ensures precise dimensions. The fittings undergo polishing for a smooth finish, followed by surface treatments like electroplating. Finally, each piece is inspected for quality assurance. The precise production of a brass fitting bracket. The process includes cutting brass rods, CNC machining, deburring, polishing, and threading. Each step ensures high-quality parts with accurate dimensions and a smooth, shiny finish. The automatic LPG valve assembly machine efficiently assembles components with high precision. First, parts such as valve bodies and springs are fed into the machine through vibrating feeders. Robotic arms and pneumatic systems accurately position each part. The assembly process involves inserting springs, valve pins, seals, and tightening caps. Sensors monitor each step to ensure proper assembly and detect faulty units. Completed valves are automatically transferred to the inspection area. The machine operates continuously and reduces labor, ensuring consistent quality and increased productivity in LPG valve manufacturing. The brass valve production industry plays a critical role in plumbing, HVAC, and industrial applications, with global demand surpassing 1.2 billion units annually. Brass valves are favored for their corrosion resistance, machinability, and durability. Typically made from alloys containing 60 to 70% copper and 30 to 40% zinc, these valves are manufactured through forging or casting processes. In 2023, the global brass valve market was valued at approximately $3.8 billion United States dollars, with projections indicating a CAGR of 4.5% through 2030. Major production hubs include China, which accounts for over 40% of global output, followed by India, Germany, and the United States. Production begins with hot forging, where billets are heated to around 750 to 850 degrees Celsius and formed under 300 to 800 ton presses. After trimming and shot blasting, precision CNC machining ensures tolerances within plus or minus 0.01 millimeters. Surface finishing and chrome or nickel plating enhance appearance and durability. Each valve undergoes pressure testing at 1.5 to 2 times the rated working pressure, often 16 to 25 bars. Automation has improved throughput, with modern plants producing up to 10,000 valves per day. As water conservation and sustainable materials become priorities, innovations in lead-free brass and smart valve integration are driving next-generation development. The Revax D16 wire bending machine operates by manually feeding a rod into the machine. Once inserted, the machine's CN-controlled bending head executes precise bends according to programmed specifications. The process involves sequential bending operations to form the desired shape. After completing the bends, the machine releases the finished piece, ready for collection. This semi-automated process ensures accuracy and efficiency in wire shaping tasks. The multifunction threading and chamfering head integrates threading, chamfering, and bending into a single CNC-controlled process. It efficiently produces complex wire forms and springs with high precision, enhancing productivity in various industries. The production process of a paint roller with a plastic handle begins with forming the metal frame L-shaped from steel wire, typically 3 to 8 millimeters in diameter. The wire is straightened and cut to standard lengths, then bent into an L shape. The ends of the frame are chamfered and threaded to allow secure assembly with the plastic handle. Next, the handle is manufactured using an injection molding machine. Plastic pellets are fed into the machine, melted, and injected into a mold designed with grooves and slots for better grip and comfort. Once cooled, the handle is removed and inspected for quality. Assembly follows. The metal frame is inserted into the plastic handle using an automated system. Pneumatic pressure ensures a tight, secure fit. Finally, the roller tube is attached to the opposite end of the frame, allowing smooth rotation without jamming, completing the paint roller assembly. At U.S. Tsubaki's whole yoke plant, roller chains are expertly crafted through precision machining, heat treatment, and rigorous quality checks. Advanced automation ensures each component meets exacting standards, resulting in durable, high-performance chains that power industries worldwide.
The modern glass bottle may appear simple, but its creation is the result of a precisely engineered, highly coordinated industrial process. The glass bottle manufacturing process at Rotel follows a highly controlled sequence designed to ensure consistency, durability, and precise shaping across large production volumes. It begins with raw material preparation, where sand, soda ash, limestone, and cullet are proportioned according to strict formulation requirements. These ingredients are then conveyed to the batching and mixing stage, where automated systems verify accurate dosing to maintain uniformity across every batch. Once mixed, the materials move into the melting phase. Inside a furnace operating at approximately 1,600 degrees Celsius, the batch is transformed into molten glass, or gob. The molten gob is subsequently directed to the glass forming section, where shaping begins. Narrow-neck bottles such as beer, wine, and soda containers are formed using the blow-and-blow process. In this method, compressed air first shapes the gob into a preliminary form called a parison, which is reheated, inverted, and blown again to achieve its final geometry. For wide-mouth containers including jars, vases, and milk bottles, the press-and-blow process is preferred. Here, a plunger pushes the gob into the mold to create a parison, which is then transferred to a blow mold for reheating and final inflation. After forming, bottles enter the annealing layer, a controlled kiln where they are gradually reheated and cooled below the glass strain point to relieve internal stresses. Quality control follows, using automated rejection systems and trained visual inspection to eliminate defects such as thin walls, blisters, seams, deformation, or surface imperfections. Completed bottles undergo surface treatment for enhanced durability and scratch resistance before moving to packaging.
Super Radiator Coil specializes in the custom design and manufacture of high-performance heat exchanger coils and air coolers for a wide spectrum of industrial applications. Each project begins with detailed consultation, where engineering teams assess thermal requirements, dimensional constraints, material specifications, and installation conditions. Designs are verified using a proprietary wind tunnel testing lab, capable of simulating real-world operating environments with controlled refrigerant circulation. Manufacturing is carried out across multiple facilities equipped for high-precision fabrication. Tubes, fins, and headers are formed from application-specific metals. Tubes are hydraulically expanded to maximize surface contact with fins, enhancing heat transfer efficiency. All brazed or welded joints undergo thorough leak detection and quality inspection. Custom air coolers produced at the Phoenix plant are designed to withstand corrosive environments in demanding systems such as compressors, oil cooling units, and HVAC applications. Additionally, Super Radiator Coils is one of only 3 global producers certified to manufacture nuclear safety-related coils. An advanced turning milling component made from C45 steel is precisely machined on the Okuma Multis CNC turning center. The process begins with clamping the steel workpiece securely in the chuck. High-speed turning operations shape the outer contours, followed by milling to create complex geometries, including holes and slots. The Multis BII's multi-axis capabilities allow for seamless transitions between operations, ensuring high accuracy and surface quality. Thanks to the machine's automatic tool changer and synchronized movements, setup time is reduced and production efficiency is enhanced. This integration of turning and milling on a single machine minimizes repositioning, making it ideal for producing complex steel parts in a single setup. The Orion Valves PAM, a large-sized boring and milling machine, is engineered for precision machining of sizable industrial components. The process begins by securely mounting the large valve body onto the machine's work table. The operator then programs the machine to execute specific boring and milling operations. The machine spindle, equipped with appropriate cutting tools, performs precise boring to create accurate holes, followed by milling to achieve the desired surface finish and dimensions. Throughout the process, the machine ensures high accuracy and repeatability, essential for producing components that meet stringent industrial standards. This integrated approach streamlines production, reduces manual intervention, and enhances overall efficiency in manufacturing large-scale valve components. PrimeTurning technology from Sandvik Coromant, fully integrated into Mastercam 2020, enables maximum productivity in turning operations. This advanced technique allows for flexible machining in all feed directions, significantly enhancing operational efficiency. The optimized chip evacuation system reduces the risk of chip entanglement, ensuring smooth material removal and minimizing tool wear. As a result, tool life is maximized, leading to longer uninterrupted production runs. Additionally, PrimeTurning reduces setup times and minimizes the need for frequent tool changes, streamlining the overall workflow. Its intelligent programming within Mastercam provides users with powerful control over tool paths, enabling efficient, safe, and precise turning. With these capabilities, manufacturers benefit from improved throughput, reduced costs, and enhanced machining flexibility, making PrimeTurning an ideal solution for high-performance turning applications. Turncut and 5-axis auto-tuning on Okuma Multis U4000. The turncut process synchronizes spindle rotation and tool movement to machine complex contours. Next, the 5-axis auto-tuning system calibrates geometric accuracy using a master ball. The probe measures multiple points at various B and C axis angles. The system analyzes deviations, calculates alignment errors, and generates compensation values. These values are stored in the control system to ensure high-precision machining in future operations. The MC200 pipe and profile bending machine operates with 3 rollers arranged in a pyramid configuration. In the beginning, the operator positions the pipe between the lower and upper rollers. By adjusting the top roller downward using the hand wheel, pressure is applied to begin the bending process. The side rollers are powered and rotate in opposite directions, feeding the pipe through and creating a gradual curve. For tighter curves, the operator incrementally lowers the central roller between passes, allowing for greater deformation with each cycle. The machine is equipped with adjustable rollers to accommodate round pipes, square tubes, and profiles of various sizes. The control panel allows for forward and reverse rotation, ensuring precise shaping and easy removal of the workpiece. This cold bending process does not require heating the material and maintains the integrity of the pipe. The MC200 is commonly used for making circular frames, arches, and structural components in metal fabrication and construction industries. The process begins with a flat, circular aluminum blank, 2 mm thick, mounted onto a spinning lathe. A mandrel defines the final shape, and the operator uses scissor tools to press the blank against the mandrel as it rotates. These tools reduce physical effort due to the pivot mechanism, making the process less labor-intensive. Through controlled force, the aluminium conforms to the desired shape, meeting precise dimensional requirements. Once formed, the component is deburred to remove sharp edges. After additional fabrication and quality inspection, the base is ready for use in the electrical hub assembly. The silver cup is crafted through a metal spinning process. A flat silver disc is mounted on a lathe and spun at high speed. Using a forming tool, the artisan applies pressure, shaping the metal over a mandrel to achieve the desired cup form. This technique allows for seamless, symmetrical designs, combining precision with traditional craftsmanship. Copper sheets are first cut and shaped into decorative panels. These panels are then carefully bent and soldered together to form the lantern's frame. Holes are drilled for assembly, and edges are smoothed. Afterward, the lantern is cleaned and polished for a refined look. Glass panes are inserted into the frame, and metal components are riveted or screwed in place. The finished copper lantern is both functional and ornamental. The handmade water container is crafted from a flat metal sheet. First, the craftsman marks and cuts a circular piece of sheet metal. The disc is then placed on a spinning lathe. Using various handheld tools, the worker gradually shapes the spinning metal into a cylindrical form. After forming the main body, the base is created separately and welded to the cylinder. The top part is trimmed and smoothed for a neat finish. Next, the spout is formed and welded to the body. The handle is also made and attached by welding. After all components are assembled, the joints are polished. Finally, the entire container is cleaned and checked for leaks. This process requires skillful handwork, attention to detail, and precision to ensure the container is functional and aesthetically pleasing. At the electrophone, the production of brass bells begins with flat brass sheets. These sheets are first precisely cut to size. They are then heated to make the metal more malleable and easier to work with. Once softened, the sheets are carefully hand-hammered into a rough bell shape. The next stage is spinning. This process involves rotating the metal on a lathe while shaping it with tools to form the final bell contour. Skilled artisans continue to refine the bell's shape with additional hammering. Following the formation of the bell, other key parts of the instrument, including the lead pipe and valve section, are assembled. Each component is aligned and soldered by hand to ensure accuracy. Special attention is given to the valves, which must move smoothly and seal perfectly. Brass tubing is shaped using mandrels and filled with a stabilizing material during bending to prevent deformation or wrinkling. Once the instrument is fully assembled, it undergoes polishing and cleaning. Finally, it receives a durable, high-gloss lacquer or a silver-plated finish to protect the surface and enhance its appearance. A copper disc is spun on a lathe, shaped over a mandrel with tools, gradually forming a symmetrical vase through applied pressure. This technique involves mounting a flat copper disc onto a lathe, where it's rotated at high speeds. The special tool radius U-channel is a precision-engineered cutting tool designed to mill U-shaped channels with a defined radius. Commonly used in mold making and component profiling, it ensures consistent curvature, smooth internal surfaces, and accurate dimensional control in both soft and hard materials across various industries. The Rottler VR7 valve refacing machine delivers precision machining for both small and large diameter valves with unmatched surface finish quality. Engineered with linear roller-bearing slideways, the system ensures ultra-smooth, accurate movement, eliminating backlash and guaranteeing long-term alignment stability. This advanced design enhances concentricity, CONCEN, between the valve face and stem, producing consistent, mirror-like finishes essential for optimal valve sealing and performance. The VR7 accommodates a wide range of valve sizes, from motorcycle to heavy-duty diesel applications. For small diameter valves, the machine provides excellent rigidity and support, while large valves are securely clamped with precision. Adjustable stops enable repeatable machining with features like an equal-width chamfer stop, ensuring consistent seating geometry on every valve. The integrated V-stop ensures equal valve length by locating the valve stem with exact positioning each cycle. Quick change tooling, digital micrometer adjustments, and quiet operation further streamline the process. Whether for high-volume production or custom performance work, the Rottler VR7 stands out as a premier valve refacing solution, combining mechanical reliability with high-precision engineering for the demands of today's engine rebuilders.
Circular saw blade manufacturing is executed through a tightly sequenced, engineering-driven workflow designed to ensure structural stability, cutting precision, and repeatable performance under high-load operation. Production initiates with laser cutting of the metal plate, where CNC-controlled optics deliver profile accuracy within narrow tolerances. Stamping operations then form expansion slots and stress relief geometries essential for thermal stability. The blanks proceed to heat treatment, consisting of a controlled hardening cycle followed by tempering. This metallurgical conditioning increases hardness while maintaining the toughness required to prevent microfractures during high-speed rotation. Post-treatment, the blades undergo coarse plate polishing and teeth-base grinding, establishing planar accuracy and uniform carbide seating surfaces. A comprehensive plate inspection verifies flatness, hardness distribution, and internal tension. In the tipping phase, precision carbide teeth soldering attaches tungsten carbide inserts using automated induction systems. The blades are then sandblasted, converted into half-ground condition, and subjected to industrial cleaning. Stress line processing and precise adjustment calibrate internal tension zones. An evenness inspection confirms runout parameters. Inside the teeth grinding workshop, sequential machining includes front rake grinding, back rake grinding, and rake angle examination to ensure accurate chip evacuation geometry. Side rake inspection and fine grinding deliver final cutting profiles with micron-level precision. Final processes encompass laser marking, silk printing, and packaging. Each blade must pass a controlled cutting test, validating stability, vibration behavior, and edge retention performance before release.
This company specializes in producing durable, precision-engineered aluminum products, including versatile profiles for industry, high-performance doors and curtain walls for buildings, and hygienic, eco-friendly packaging solutions for food, pharmaceutical, and cosmetic applications. The UBC recycling machine processes aluminum cans through shredding, paint removal, melting, and purification. Aluminum wheels are fed into a hammer mill, where rotating hammers crush them into smaller fragments. These fragments are then separated by a magnetic separator, removing ferrous metals. The remaining non-ferrous aluminum pieces are collected. The aluminum rotor recycling process involves a hammer mill that crushes rotors into smaller pieces. These fragments are then passed through a magnetic separator, which extracts ferrous materials. The remaining non-ferrous metals, primarily aluminum, are collected for further recycling. This efficient method ensures effective separation and maximizes material recovery.
The production of a large generator shaft at Sarschmiede GmbH in Völklingen is an intense combination of heat, force, and precision engineering. Within the electric steelmaking plant, steel workers operate in an environment dominated by fire, molten metal, and heavy machinery. Despite modern automation, the forging of an 80-ton generator shaft still demands substantial manual expertise. The process begins in the electric arc furnace, where the molten steel reaches temperatures exceeding 1,700 degrees Celsius. Once the melt achieves its defined metallurgical composition, an internal trade secret, it is tapped into a ladle and guided into the casting mold, forming the initial rough ingot. After solidification, the massive steel blank is transferred into a hearth furnace. These industrial furnaces consume as much heating gas per day as a small town, underscoring the immense energy required. Handling such a glowing block is extremely delicate. If it slips from the crane's gripping tongs, it could cause catastrophic damage. Sarschmiede operates one of the world's most advanced freeform forges, equipped with crane systems and manipulators capable of lifting components weighing up to 165 tons. Inside the control cabin, the crane operator and the press operator coordinate their motions. The forging plan for each generator shaft spans approximately 1 week. The first operation involves forming a gripping stub so the manipulator can securely rotate and position the workpiece. During the stretching, or drawing out stage, the hydraulic forging press applies controlled pressure up to 75,000 tons to lengthen the steel blank with millimeter accuracy. As the slag detaches from the surface under pressure, workers remove residues with compressed air to maintain surface cleanliness. Each forging cycle follows a sequence of heating, pressing, and dimensional checks. This repeated thermal mechanical treatment densifies the internal grain structure of the steel, much like kneading dough to eliminate voids. When the temperature drops too low for continued forging, the shaft returns to the furnace. Meanwhile, press saddles are exchanged to support the next forming stage. Subsequently, the ingot undergoes upsetting, in which it is positioned vertically and compressed to increase cross-sectional density. Once completed, the piece is returned to a horizontal position and enters the second stretching phase. At this stage, both the manipulator and the auxiliary forging crane stabilize the workpiece to prevent bending, as thousands of tons of force shape it to its defined profile. Surface imperfections and internal fissures are removed through oxygen-assisted melting. The forged ends contain head and foot scrap, which is cut away and recycled into the melting process. The semi-finished shaft is reheated once more before undergoing its critical hardening phase. Immersion into a massive water quench tank. The 13-meter-long, 80-ton shaft must be lowered with absolute stability to achieve the required metallurgical properties. Final machining removes up to 14 centimeters of steel, achieving dimensional tolerances within half a millimeter. Saarschmiede manufactures more than 200 generator and turbine shafts annually, supplying power plants and large marine engines. Each shaft represents an investment of precision, energy, and craftsmanship, with an average value of approximately 200,000 euros.
The casting of a new bell for Inverness Cathedral is a detailed and traditional process. It begins with designing the bell's profile and tonal characteristics. Craftsmen create a bell-shaped core from bricks and clay, followed by a wax or false bell layer that forms the exact shape and decorations. Over this, they build the outer mold, called the cope. Once the mold dries and hardens, it is heated to remove the wax, leaving a cavity between the core and cope. Molten bronze, an alloy of copper and tin, is then poured into this cavity. After cooling for several days, the mold is broken to reveal the rough bell. The bell is then cleaned, tuned by carefully removing material from the inside, and fitted with a clapper. Decorative inscriptions or patterns may be added. Finally, the finished bell is delivered and installed at the cathedral, ready to ring for generations to come, continuing a centuries-old tradition of craftsmanship and spiritual resonance.
The lost foam casting process begins with making white foam models from expandable polystyrene beads. These beads are pre-foamed, ripened, molded, cut, and bonded to create accurate patterns. The EPS beads are carefully selected based on size and density to ensure precision. After molding, the foam models are coated with a special refractory coating that insulates the molten metal. The coated models are dried in controlled conditions to prevent deformation. Next, the coated foam models are placed into sand-filled flasks using vibration tables to compact the sand around them. Molten metal is poured into the mold under negative pressure, causing the foam to vaporize and be replaced by the metal, forming the final casting. After cooling, castings are removed and sand is recycled through a treatment system. Vedanta's Logigar Alumina Refinery secures 95% pump availability by outsourcing life cycle services, remote monitoring, condition-based maintenance, and rapid spares logistics. Continuous vibration, pressure, and temperature analytics flag incipient faults, minimizing unplanned downtime and sustaining nameplate hydrate throughput. At VMB, valve production follows a tightly sequenced, vertically integrated workflow. Engineers begin with 3D design and solid flow casting simulation to optimize gating. Wax patterns are produced by high-pressure injection, then chased, gated, and ceramic dipped to build a refractory shell for the lost wax process. After dewaxing, shells are sintered to full strength, and alloy is melted in an induction furnace and poured under inert gas. Once solidified, the ceramic is knocked out, gates are removed, and castings pass shot blasting and solution heat treatment. Statistical quality control, spectrometry, UT, and dye penetrant precedes CNC machining of bodies, bonnets, and internals. Finished components are assembled with precision lapping of seats and plugs, followed by hydrostatic and pneumatic pressure tests to API standards. Finally, valves receive anti-corrosion coating in a controlled paint booth, cure in a bake oven, and move to final inspection and packaging for worldwide shipment.
Inside the world-class Volvo bus factory, operated by Tata Autocomp Systems (TAB) in India, precision manufacturing merges with cutting-edge technology to deliver premium-grade buses for national and global transport fleets. The facility integrates advanced automation, high-speed production lines, and rigorous quality control to meet Volvo's global standards. Production begins with chassis fabrication, where high-tensile steel is shaped, welded, and assembled using robotic arms and CNC position fixtures. The process ensures perfect structural alignment and high torsional strength, forming a reliable base for the bus body. In the body assembly section, preformed roof modules, side panels, and flooring structures are joined with the chassis. Using a combination of laser cutting, automated riveting, and adhesive bonding, the outer skeleton is constructed for maximum strength and precision. Lightweight alloys and composites help reduce overall vehicle weight while maintaining structural integrity. After this, the vehicles are transferred to the finishing zone, where door frames are precisely fitted into pre-cut cavities using guided mounting systems. Each glass window, including windshields and side glazing, is installed using robotic suction arms and fast curing adhesives, ensuring airtight seals and impact resistance. Lighting systems, including headlights, tail lamps, indicator modules, and internal wiring for exterior lights, are integrated next. These systems undergo electrical integrity checks and are aligned using calibrated fixtures to meet road safety regulations. Once the frame, glazing, and lighting are complete, the buses enter the automated paint line, where multi-stage coating provides corrosion resistance and uniform aesthetics. Each bus is finally tested for braking, suspension, and steering through simulated road conditions. Through advanced engineering and local global collaboration, the Volvo TAB India facility is setting benchmarks in bus manufacturing technology and public transport excellence. At Rolls-Royce, building a jumbo jet engine like the Trent series is a combination of cutting-edge engineering, global logistics, and 24/7 real-time monitoring. At peak times, engineers track data from up to 10,000 engines simultaneously, monitoring critical indicators such as vibration, pressure, and temperature. With over 1.5 million measurements received daily, anomalies are instantly flagged by automated systems. Experienced help desk engineers, many with hands-on military and aerospace backgrounds, support maintenance crews worldwide. On the assembly line, each engine is built in modular stages. Delays, such as the late arrival of a vital turbine module, can stall production. However, engineers adapt quickly, fitting components out of sequence to maintain workflow. Critical modules, like the fan cage or turbine drive, are installed with micron-level precision. In Warwickshire, fan case manufacturing is underway for a record-breaking Trent engine. The fan case, with a diameter of 118 inches, is the largest Rolls-Royce has ever produced. These components will be part of a next-generation engine, with reduced carbon emissions, designed to power the Airbus A330 and Boeing 787. Quality assurance is paramount. Before delivery, engines undergo borescope inspections, a type of keyhole engineering surgery, to ensure the internal blades and combustion chambers meet strict standards. Apprentice engineers learn alongside veterans, contributing to projects while preserving British manufacturing skills. Once approved, engines are shipped to aircraft manufacturers worldwide. During a historic moment, engineers at Derby watch live as a new Boeing Dreamliner takes off, powered by their Trent 1000 engines. With continued innovation and strong global demand, Rolls-Royce remains at the forefront of jet engine technology, delivering performance, efficiency, and reliability for the aviation world.
Xishang's Machining Center deploys heavy-duty CNC vertical lathes, double-column boring milling machines, 5-axis gantry mills, and CNC gear hobbing machines. Twin 8-meter swing vertical lathes rough and finish turn kiln tires and girth gears up to 150 T. A 5 meters travel floor borer tackles deep hole drilling and precision facing, while a 6 meters bed gantry mill handles surfacing of rolling mill housings. Gear hobbing cells cut module 32 spur or helical teeth in a single setup, guaranteeing 6 to 7 grade accuracy per ISO 1328.